All right, so topic 9.4 is going to be about resolution. It's actually a relatively small topic, so shouldn't take us too long to get through it. Let's take a look at the essential idea of this unit. Resolution places an absolute limit on the extent to which an optical or other system can separate images of objects. That's what resolution means. Can you see two distinct things as being distinct, or do they meld and merge into one, appearing to be one object? That's the idea of resolution. Note the nature of science. It has to do with improved technology. The Rayleigh criterion is the limit of resolution. Continuing advancement in technology, such as large diameter dishes or lenses, or the use of smaller wavelength lasers, pushes the limits of what we can resolve. Cool. A couple of things you need to understand there: the size of a diffraction aperture, the resolution of simple monochromatic two-source systems. Application of skills: you should be able to solve problems using the Rayleigh criterion, and you should be able to deal with resolvents of diffraction gratings. We'll talk about that. Notice the guidance there. The proof of the diffraction grating resolvents equation is not required. You won't have to derive the equation, and there are two equations that we'll be working with in this unit. So let's just start by talking about resolution and the Rayleigh criterion. As I mentioned earlier, resolution, the concept of resolution is this. It's the ability to see two distinct objects as being distinct rather than them melding into one another. And these diagrams at the bottom of this slide go through what that looks like. Notice that, remember that when light passes through an opening, it diffracts, single slit diffraction. So that's kind of what we're talking here. Remember what that diffraction pattern looked like. Back in our single slit diffraction unit, we talked a little bit about graphs like this, where the intensity of light that passes through a single opening spreads out and creates a diffraction pattern with a bright central maximum, and then a dark spot, and then another bright spot, bright spot, and so on. Well, this is going to limit what will allow you to see. So let's take a look at this diagram here in the bottom left-hand corner. Notice that if we're looking at two things and the light passes through a single slit, that if the diffraction patterns, and that's what these dotted lines are that you see here, these dotted lines that go down, those are the single slit diffraction patterns of each individual object. If those diffraction patterns do not overlap, you'll see two distinct objects. As they get closer and closer together, or farther and farther away, the diffraction patterns get closer and closer together, and you start to get a situation here. This is known as the Rayleigh criterion. Notice there's a little dip in between the two diffraction patterns so that you can still distinguish that there are two separate things. And if the two objects, their single slit diffraction patterns, are so close together that when they combine, they make one large bright spot, you're not going to see two separate things. That's the concept behind resolution. What it looks like visibly is more like this. Now notice something first also about these diffraction patterns. These are circular diffraction patterns. So instead of having a vertical slit or a rectangular slit that light's passing through, we're talking now about circular openings, kind of like the pupil of your eyes. Notice that the diffraction pattern is bright, dark, and so on. So you get these circular diffraction patterns. In this image, the two diffraction patterns do not overlap, so you can see the two distinct things. Here, they're getting closer and closer together. They're barely distinguishable because there's a slight dip between the two diffraction patterns. And here we would say, nope, you can't resolve those two things. It appears to be one object, even though there are two separate objects creating diffraction patterns on your retina or on the film that you're using in your camera or whatever it might be. So what we're talking about here is that the resolution of objects is limited due to the diffraction patterns that are created, the diffraction of light as it passes through the opening. And usually we're talking about your pupil, but it could be other openings, again, with telescopes or cameras or microscopes or whatever it might be. So there's this thing known as the Rayleigh criterion that you need to be familiar with. And the Rayleigh criterion basically states when two objects, the limit of resolution, how close their diffraction patterns can appear so that they can still be resolvable. And the criterion is this: if the central peak of one of the diffraction patterns of one of the objects, if it aligns with the first minimum of the other one, then the objects are barely resolvable. So the Rayleigh criterion says that when the objects their diffraction patterns are far enough apart so that the central maximum of one is no closer than the first minimum of the other one, then you can resolve the two objects. If they get closer together than that, you cannot resolve them. And that's known as the Rayleigh criterion. So let's try to talk about some examples here so that we can see, you can try to get a grasp on what the heck we're talking about here. First example is an easiest one, I think, to comprehend, are car headlights. So imagine you're out in the salt flats of Nevada or Utah, really, really flat horizon, far, far away. And let's say there's a car, it's at nighttime, and it's facing you, and it's got its headlights on. And you can see two distinct headlights, no problem. You can resolve them as being two distinct lights. If someone puts that car in reverse and starts backing away from you, and we're talking huge distances here, backing away, those headlights will appear to get closer and closer and closer and closer together. And at some distance away, those headlights will no longer appear as two lights to you. They will appear as one single light. And at that point, you are no longer capable of resolving them anymore, of detecting them as individual lights. So that's the best example that's kind of tangible. There's a lot of other examples as well. Stars in the sky, another classic one. When you walk out at night here in Aspen, Colorado, and look up at those beautiful stars in the sky, you can see many, many, many stars. Actually, about 2,500 of them on a good clear night, right? At any given time. You look up, you see about 2,500 stars. Well, most of those, more than half of them, are actually binaries. Two or more stars that are orbiting a common center of gravity. And yet your eye cannot detect that, cannot resolve them as being individual stars. Instead, you see the binaries as being one point of light because they are so distant and so close together from that perspective that your eye only sees one pattern, and therefore you think of them as being single stars. But in fact, there's many more stars out there. It's just that you're not able to resolve them. Spy satellites, often a fun example. But when evil government scientists are making spy satellites, one of the things they're doing is they're trying to take images of as precise as they can, of as fine of detail as they can. And what limits them is their ability to resolve things. So oftentimes you'll hear them saying, oh, you can see a penny from 20 miles away. Well, that's basically giving you an idea of what the resolution of those cameras are and how well they are able to resolve objects. And then, of course, we've got things like microscopes, telescopes, electron microscopes, all sorts of things that help increase our ability to resolve objects, right? You can't see individual bacteria, but with certain kinds of microscopes, you can resolve them and actually see them. You can't see binary stars, but with certain kinds of telescopes, you can resolve them and actually see them with your naked eye, that they are more than one star. Electron microscopes use even smaller things and smaller wavelengths allow you to probe objects with a higher resolution. So using like a smaller wavelength laser, like a blue laser instead of a red laser, can help with resolution. And electrons, what we'll learn later is that electrons actually have wavelengths as well, and their wavelengths are quite small. So if you use electrons to try to resolve small objects, you can even do so more precisely. So as we're getting into the mathematics of this topic, there's one thing that's gonna be really helpful to differentiate, and your textbook does a good job of doing this. But the idea of angular separation versus single slit diffraction angle. These are two different angles, okay? And angular separation is just the angle apart that things appear from your perspective. So this is a very crude diagram of a galaxy. Imagine this being a galaxy. It has a certain amount of width, right? And the angle that width appears to you is what's known as the angular separation. Imagine instead of this being a galaxy, if these were two stars, how far apart they are would be their angular separation. And notice there's different things that will change this angle. If you were to get closer, the angular separation would get larger, right? If you're standing right here, suddenly you have a much larger angle of separation. Another thing that can happen is the objects can get farther apart, and that can change their angle of separation. So mathematically, it's relatively simple. But angular separation, that angle will just be S over D. S being how far apart the objects are, or how big how wide the galaxy is, and D, in this case we use a lowercase d, is basically how far away it is. And if you do that math, you will get the angular separation in radians. It's kind of nice, kind of simple. In astronomy, we'll talk about the angular width or angular separation of things quite a bit. And just to give you an example, the full moon has an angular width of about 1/2 of a degree. It means it takes up about 1/2 of a degree in the night sky from our perspective. If you hold out your index finger at arm's length, the width of the tip of your index finger is about 1 degree. So imagine that the full moon is actually about half that width. And I know it doesn't seem like that's realistic, but try it out next time you have a full moon. See what you can see if that works for you. Now, when we were talking about single slit diffraction, we had a different angle that we were talking about. And that angle was calculated using wavelength divided by b, which is the width of the opening that the light passed through. And remember, for that angle, we were talking about the angle from the middle of the central maximum to the first dark spot. Let me draw that and show you what I'm talking about. So if this is a graph of the intensity of light versus angle of light passing through a single slit and diffracting, the angle that we calculate using that equation is from the middle of the central maximum to the first dark spot. So basically, the angle of the calculation is half of the width of the central bright spot of the diffraction pattern. Now, if the slit that the light is going through is not linear or rectilinear, it's not like a rectangle or vertical sided slit. If instead if it's a circular opening, this equation changes just slightly. Basically, we don't have to get into the details of it, but all we have to do is multiply by 1.22. So this is the diffraction angle for a circular slit diffraction and, circular opening diffraction. And this equation is in your data booklet in this topic 9.4. So that's what it means. It's the same as single slit diffraction, and we just added a multiplier of 1.22 to deal with the fact that if it's going through a circular opening, like your pupil, this is the diffraction pattern angle that will be created. So ultimately, what we'll deal with mathematically is that the resolution of two objects will occur when the angular separation is equal to or greater than this diffraction angle, because that's when the diffraction patterns will meet the Rayleigh criterion of the central peak being aligned. If it's equal to, the central peak of the diffraction pattern will be aligned with the first minimum of the other pattern. If it's greater than that, then you can definitely resolve the two objects. So simply, equating these two things, S over D has to be equal to or greater than 1.22 lambda over B will dictate whether or not resolution occurs. All right, so that particular relationship is not in your data booklet, but there you go. All right, here's an IB question to practice with, dealing with resolution. Hit pause, work it out, see what you can get, and we'll go through it here in just a few seconds. Okay, so we'll go through this one. Relatively straightforward, I think. Basically, we're just using the basic equation that theta is equal to 1.22 lambda over b. So the first thing to be careful of is making sure that when you're plugging in the wavelength, you notice that it's in centimeters. So convert that to meters. 20 centimeters is going to be 0.2 meters. And you'll end up with 0.048 radians, which leads you to answer A. Okay, here's another IB question for you. Hit pause, take a look at it, give yourself 90 seconds, see if you can solve it. It basically is dealing with the Rayleigh criterion that we talked about. All right, going for the answer here. Notice that the definition of the Rayleigh criterion is where the first minimum of one diffraction pattern coincides with the central maximum of the other diffraction pattern, or C. That is correct. Okay, here's an IB practice problem that is not multiple choice in nature. It's more mathematical. You see the point values there on the right, 2 points, 3 points, and 2 points, respectively. Hit pause, work through this, see what you can do, and then we'll go through it. All right, hopefully you were able to sketch this graph, because I've been sketching it for you throughout this one, and it was a topic we discovered earlier. But you want a central maximum, you want to make sure that you go to 0 at some point, and then have another little maximum, and so on. So what they're looking for here for the 2 points is that these go actually to 0, and that the subsequent bright spots are less than 25% of the initial central maximum. So, and that's just by eyeball. Those are for the 2 points there. For question B, you basically are just explaining the Rayleigh criterion as best you can in your own words. And it is a 3-point question, so hopefully you bring up some of these things in your explanation. If you had some sort of explanation of resolving and what that means, basically being able to see two images as being separate, that's a point. If you talked about diffraction patterns overlapping, that would be another point. And then if you mentioned that the central maximum of one of the patterns is at least as far away from its companion as the first minimum, then that's the third point. There you go. And for question C, you're going to have to do a little bit of math here. Let's work it out. So here we're going to be using the two equations here. This is our angle for diffraction. This is going to be basically our angle, it's going to be our angular separation, and we're going to be solving for x here. They gave us all the other variables. When we do the solving, we get a solution of x equals 0.43 meters. Okay, hope that worked out for you. So the last little bit of this topic has to do with diffraction gratings and the resolution of diffraction gratings. You might recall that a diffraction grating is when you have multiple slits very close together and light passes through them and it diffracts. You get very distinct bright spots, and the more slits you have and the closer together they are, the intermediary little bright spots go away and you end up just with very distinct bands of bright line. Now, one of the cool things about diffraction gratings is that they can resolve spectral lines that are incredibly close together, have very similar wavelengths. And this is useful whenever we send spacecraft out to explore other planets or other stars and things like that. They use what are called spectrometers. And diffraction gratings are a part of the spectrometer. And what they're trying to do is measure wavelengths of light coming from or off of these sources, because you can learn all sorts of things about planets and about objects in space just by observing their light. So this is what diffraction gratings and spectrometers do. So the resolving power of a diffraction grating, it's also known as the resolvance, is equal to R, and that is equal to the average wavelength divided by delta lambda, or the difference in wavelength that you're trying to resolve. So that's a pretty basic equation. You take the average of the two wavelengths that you're trying to resolve. Delta is the difference between them, how far apart they are. So the more resolving power you have, right, since this is a fraction, the smaller this number, the bigger this one. So if I have a higher resolvance or higher resolving power, I can differentiate between wavelengths or spectral lines that are closer together. Now, it just so happens that resolvance R is also equal to m times n, where m is the order at which the spectral lines are observed. Remember, when light passes through a diffraction grating, you get multiple bright spots, and those are the different orders, first, second, third, fourth, so on. N is the number of lines per slit. When we were doing the experiment in class with the green laser and trying to predict where the bright spots would be on the screen, I think we were using a diffraction grating that had something like 600 slits per millimeter. I mean, incredibly close together, and they can get even more fine than that. So we can set these equations to be equal to one another, and we can solve for delta lambda and basically discover that the more lines per centimeter or millimeter, the closer the slits are together on my diffraction grating, the better resolution I get. And this equation is in your data booklet. Actually, what you'll find in your data booklet looks something like this. R equals lambda average over delta lambda, which equals m times n. In topic 9.4, that's your second equation. Okay, so here is a multiple choice, IB multiple choice question dealing with the resolvance of a diffraction grating. Hit pause, try it out, see what you get. All right, so notice that they're asking for what is, so notice they're saying, what is the minimum wavelength difference? Minimum wavelength difference. So what we're looking for is delta lambda. And I can take the equation from the data booklet and rearrange it to get delta lambda equals average lambda over mn. So they give us the wavelength, they give us the number of slits, they give us that it's the second order. And when doing all that, throw the math together, you'll get the answer B, 2 nanometers. Okay, let's take a look at the syllabus here, make sure we covered everything. We did talk about the size of a diffraction aperture and the resolution of simple monochromatic two-source systems. Basically, it's all about resolution. Can you solve problems with the Rayleigh criterion for light emitted by two sources, diffracted at a single slit? That's the equation we were working with. And do you understand about resolvents of diffraction gratings? That's the second equation. We talked about both the equations. Should be good. Let me know if you have questions.